Hello, everybody, and welcome to our continued conversation about chemical equilibrium. We, in our last few series, discussed kind of the concept of equilibrium and began to have a conversation about the equilibrium constant, which is our primary means of describing mathematically or numerically what's happening with a system at equilibrium. So you can recall that we defined our equilibrium constant, KEQ, to be a proportion of our product concentrations at equilibrium to our reactant concentrations at equilibrium. And by understanding the nature or the value of our equilibrium constant, KEQ, we can describe what's going on in terms of whether at equilibrium we have higher amounts of reactant or higher amounts of product that are present. Because remember, when we achieve equilibrium, while our concentrations of our reactant and product themselves are constant, they are not necessarily equivalent. So let's get into this idea of the equilibrium constant a little bit more in depth. So we are quantifying chemical equilibrium. And the first way we're going to do this is we are going to specify a few different forms that the equilibrium constant, KEQ, can take. So the first one is Kc, which is specifically defined to be an equilibrium constant that we're going to use here for aqueous reactions. But in general, Kc is the equilibrium constant that is specifically expressed in terms of concentration, hence the C. So Kc, this means that we are expressed in terms of concentration or molarity, which is why I've said this is what we're going to be calling our equilibrium constant when we're talking about things in solution, because when we are looking at aqueous reactions, we quantify stoichiometrically what's going on in those reactions in solution by looking at their concentration changes. So recall that KEQ is a constant value, and that is always going to be a proportion of products raised to their stoichiometric coefficients to reactants raised to their stoichiometric coefficients. So X and Y would be our balanced chemical equations coefficients. So if we're talking about Kc, this is going to look incredibly similar to our general definition of KEQ before. Kc would be equal to the concentration of our product at equilibrium over our concentration of reactant at equilibrium. So Kc, again, is equivalent to KEQ. It's just all of our amounts of things that we're looking at proportion of, reactant product, are expressed in terms of molarity. So for example, if we wanted to write a Kc expression or an equilibrium constant expression for the following complexation, let's look at a copper ion complex. We've seen a few complexes in lab already, but I don't think we've seen this one yet. So let's take a look. Let's see here. Yeah, we want this one. Okay, so we're going to show the net ionic equation of copper 2 ion reacting with 4 ammonias. In solution to create a copper ammonia complex ion. So we've got our balanced chemical equation. We are existing in a state of equilibrium, as we're going to assume now from this point forward in Chem 220 that all chemical reactions are. So if I wanted to craft an equilibrium constant expression for this, I know that I would be looking for a concentration of my products raised to their coefficients at equilibrium over my reactant concentration at equilibrium raised to their coefficients. So in this case, our product is our complex ion. So in the numerator, we would have our concentration of the copper ammonia complex, specifically at equilibrium. So that is our product. And when we're crafting our equilibrium expressions, we are looking at a proportion of product to reactant. So we have two reactants here in solution. We've got our copper 2 ion. So that would be this concentration at equilibrium. And then times are presumably aqueous ammonia. So we've got ammonia in solution somehow. So we're not adding copper to pure liquid ammonia. So we've got, let's see here, our equilibrium concentration of NH3 in solution. However, we have to take note that ammonia here does not react in a 1-to-1 ratio like copper ion and the copper complex do. This is a 1-to-4 ratio. So we need to account for this 4 coefficient by raising our equilibrium concentration of ammonia to the 4th power. So I've gotten my numerator, my equilibrium concentration of products, over in my denominator, the product of my equilibrium concentrations of my reactants, and everything has been raised to their appropriate stoichiometric coefficient. So this is Kc, which is again, equilibrium constant expressed in terms of molarity. This is what we're going to be dealing with most frequently, I would argue. However, this is not the only way that we can describe a system at equilibrium. So there's another way that we can write out our equilibrium constants. And this has to do with the idea that what if we're not looking at aqueous reactions? So let's consider something called Kp, which is a way of expressing an equilibrium constant for reactions that occur like purely in the gas phase. And if we're going to look at reactions that occur in the gas phase, we don't really talk about like the molarity of gas. Like we could talk about the molar volume, meaning how many moles occupy some volume. But when we talk about like how much of a gas is present in a mixture of gases, this means we're expressing this in terms of like a partial pressure. So Kp, this is our equilibrium constant. Expressed in terms of partial pressures. So if we wanted to do a little side-by comparison, Kc were expressed in moles per liter. So again, this requires for aqueous moles over volume. And if I were to consider how this might be different, if I were looking at a gas, I need to ask myself how I can still get an expression of moles over liter. So if we remember for a gas, we describe a gas that we're presuming to behave ideally using the ideal gas equation. So PV over NT is equal to R. And if I rearrange this to solve for N over V, or moles per liter, I get that N over V is equal to P over RT. So why is this important? For a gas phase equilibrium at a set or constant temperature, this means that N over V is equal to 1 over RT times P, where this 1 over RT term, this is a constant because it's 1 over a constant times a constant. So I'm actually going to go ahead and do a replacement. Otherwise, this is going to get a little tricky when I do this math. So let's go ahead and let my variable C, which stands for constant, be equal to 1 over RT. So if I do that, then I've got N over V for a gas is equal to C times the partial pressure of that gas. So how does that relate to the equilibrium constant Kp? So let's see here. Kp is an expression of the pressure of products over the partial pressure of reactant raised to each of their stoichiometric coefficients. So that is what this means when we're talking about Kp. And what we're trying to do with this ideal gas law stuff coming back into play is we are trying to relate Kp to Kc. So like we want to have a way of being able to convert from an expression that deals exclusively with partial pressures. So this is Keq expressed with partial pressures to our Kc, which is expressed in molarities. So let's see if we can't do something with this information here. I think this is going to be helpful if we look at an example reaction. So let's look at, I don't know, let's see here, what have I not done? Let's do, I guess, A and B. Why not? So we've got A gas plus B gas in equilibrium to form C gas and D gas. If I were to write Kp out for this would be the partial pressure at equilibrium of C. So partial pressure of C at equilibrium raised to C times the partial pressure of D at equilibrium raised to D. So looking at products over reactants. That's my product numerator. And then we've got in the denominator, partial pressure of A at equilibrium raised to its stoichiometric coefficient little a times partial pressure of B at equilibrium raised to its coefficient little b. And we are trying to see if we can't convert this into a Kc expression somehow. So we're going to utilize the fact that concentration is equal to this constant 1 over RT times the partial pressures. So then K C would be equal to, okay, let's think about what we can do to get N over V, which is moles per liter. replacing in all of these pressures. So this would be our constant C times P of C of the C at equilibrium times C concentration of D at equilibrium. So that's that for C, that's that for D, over C times concentration of A at equilibrium times C times our partial pressure, excuse me, of B at equilibrium. And as you are probably starting to notice, this is getting a little grody. So since these are constant values, let's pull them out in front of our Kp expression. So I've now got, let's see here. Oh, I'm dropping some parentheses. Boop, boop. There we go. Raised to that. So now I've got, what do I have? Using exponent rules, if I distribute this, this is C raised to the C times distributing this here, C raised to the D, over distributing this here, C raised to the A times C raised to the B. So again, these are my exponent rules, which says if I have a product that is all raised to some power, then that exponent applies to both terms in the product. So all of these together in their kind of like representative constant form is shown here. And that is going to be multiplied by what's left behind, which notice is all of our partial pressures raised to their respective stoichiometric coefficients. So that is our Kp. Now remember, we said that C has a value. We know that C is equal to 1 over RT. It's just raised to different coefficients in our expression here. And so we're going to do some exponent rules. So following this way. Let's go like this. Ready? Starting over here. So this means that Kc is equal to that common constant C. And let's think about exponent rules, okay? When I've got two things multiplied, that means that I am looking at the sum of their exponents. So that's C raised to the C plus D. And then I've got that same thing, C, right? Same base C, and that is raised to A and B and multiplied in the denominator. And that being in the denominator means that I'm adding a negative. So I'm going to write this as minus A plus B, and then times Kp. And if we're going to put this all together, because I think maybe choosing C for our letter for our constant was maybe not such a great idea, let's substitute back in C. So we're kind of leaving alphabet soup land, which means that our Kc expression, or our equilibrium expression, equilibrium constant, shown in terms of moles per liter or molarity, is now going to be that 1 over RT raised to C plus D minus A plus B, all times Kp. Here, this should be Kc. And then Kp. Okay, so think I'm going to need a little bit more room. I wonder if I have. Nope, I don't. So let's see here. To summarize, how do I relate KC and KP? So KC is equal to 1 over RT raised to our coefficients, uses exponent rules, times KP. So this is how we relate the two different expressions of equilibrium constants. One with respect to partial pressures, and the other with respect to like a molar concentration. So this is a conversion between the two. Okay, in our next video, we are going to look at other ways of quantifying what's happening in a chemical reaction, maybe not necessarily at equilibrium, and then comparing that quantification to our equilibrium constants, be they ones with respect to pressure or ones with respect to concentration. And then from there, we'll begin practicing like how we can use these numerical values that describe equilibrium to our advantage, start solving some like actual stoichiometric problems involving reactions at equilibrium. So I will see you in our next video where we discuss the reaction quotient Q.